alternating series test. All right. So an alternating series is a series that flip-flops signs. All right. A lot of times when you have a series where you've got you're summing, let's say the original problems, n approaches 1 to infinity of this negative 1 to the n minus 1 over e to the n. That's the problem that they're requesting that we analyze. The question is, does this series converge? Does it converge? And this idea of an alternating series, what we want you to be able to see is if you put 1 here, you'd get negative 1 to the 0 power over e to the n. Well, this is a positive number because, I'm sorry, you put 1 here as well. Sorry about that. Put 1 here as well. But this is 1 over e. All right? And then if you put in 2 into this series, you get negative 1 to the 1 power, and this would be e to the second. Well, notice how negative 1 to the 1, that's a negative number. So this would be negative 1 over e to the second. And then if you put in, let's say n is 3. So you've got negative 1 to the, if you put in 3 here, you'd get this raised to the second, and then you'd get e to the third. So notice how what you'd get negative 1 to the second, which is a positive 1, so this would be plus 1 over e to the third. Let's just do one more term. Let's say n is 4, or excuse me, let's say n is 4. So you have negative 1 to the 4 minus 1 power. That would be 3 over e to the 4, and e to the negative 1 to the third, that is a negative 1 over e to the 4. What you'll discover as you get more and more comfortable with these series, specifically the alternating series, is anytime you have that negative 1 raised to a power, that will force this alternating of the signs, negative, positive, negative. All right, so you'd have to get comfortable. Anytime they'd ask for the alternating series, or you're examining a series in general, anytime you see this negative 1 raised to a power, you'd have to know that that's going to force an alternating series more times than not. All right, so this is our original problem. Now, what is this alternating series test? Well, this alternating series test in my textbook, let's look at page 581. Page 581. All right, alternating series test. If you can't read this, I'll read it for you. It says an alternating series will converge if only 2 conditions are met. Only 2 conditions have to be met. The 2 conditions are if the limit approaches infinity of a sub n being the part of the series that is not alternating. Let me write this out so you can see it better. The 2 conditions to test to prove convergence of an alternating series are if you've got the limit as n approaches infinity of a sub n, if that's 0, that's the first condition that would need to be met. And the second condition that would need to be met is if a, this is what the textbook says, but we'll make this clear, a sub n plus 1 has to be less than or equal to a sub n. What that means is as you continue to increase term after term after term, a sub n plus 1, a sub n plus 2, in other words, if you continue to add more and more terms as we did here, a sub n has to be decreasing. Each term has to be decreasing. All right, so what I'd like you to be able to see is you got 1 over e. Here you got 1 over e squared. Here you got 1 over e cubed. Here you got 1 over e to the 4. Each of these terms is getting smaller and smaller and smaller. So if you experience that, that's the second condition. Sometimes this is a little bit confusing, But what they're saying is you continue to increase and increment every value of n, that should be less than the previous term. So I'm hoping that you see that that is the case here. I hope you see that that's the case here. So each of these terms are getting smaller and smaller and smaller. 1 over e to the second is smaller than 1 over e. 1 over e to the third is smaller than 1 over e to the second. 1 over e to the 4 is smaller than 1 over e to the third. So each of these terms will continue to get smaller and smaller and smaller. That's the first condition, which is satisfied right there. The second condition is applying the limit of this series, not including the component of the series that is forcing the alternating. So the second condition here that we'd have to test is the limit as n approaches infinity of this series, not including the part of the series that's forcing the alternating. So for this particular problem, is the limit of 1 over e to the n, if you evaluate as n approaches infinity, is that 0? And I'd like you to be able to see here that if you make a substitution here, n is infinity, that would really cause this denominator to get very, very big, forcing the overall fraction to get very, very small, which would mean that the limit would approach 0, all right, which is the second condition of this alternating series test. So both conditions were met. The terms are getting smaller and smaller and smaller. That's the second condition. The limit as n approaches infinity of 1 over e to the n, that is approaching 0. That's the second condition. So if both those conditions are met, according to the alternating series test, you would say that this series converges. So if I were to put that in words, I would say because each consecutive let's just, for lack of a better word, let's say for each consecutive term continues to decrease. Each consecutive term continues to decrease as n, sorry about that, continues to decrease. Let me continue it on a new line. As each consecutive term continues to decrease as n increases. All right, that's the first condition. And in addition to that, and the limit as n approaches infinity of a sub n being the part of the series that did not force the alternating, and this was 0. Those are the only two conditions that needed to be proven. Because both these statements are true, you can say that the alternating series converges. All right. So that's how I prove that. All right. So I understand how, for the person who is, maybe hasn't taken Calculus 1 yet, they would find this incredibly difficult. But this is a subject that is for a Calculus 2 student. And even a Calculus 2 student would find some of these ideas very, very complicated, very demanding. And the thing I'd say to that is the more you practice, the more comfortable you'll be with these individual tests. That's a source of encouragement for someone who might be in Calc 2 and you're still finding this stuff very confusing. With anything, the more you practice, the more comfortable you will be with it. The second thing I'd like to say is, as we continue in studying these problems, one of the things that we'll discover is you can use multiple tests for individual problems. So I don't want you to think that as we did this particular problem that the only option that we had, we've done 3 problems. We've done the comparison test. I don't want you to think that the only option for that problem where we used the comparison test was only the comparison test. For individual problems, a variety of different tests could be used to get the same result. So I want you to be aware of that as we continue to move on to a different problem. I'd like to now discuss, by the way, people who are just tuning in, one of my former students sent me some problems to go through. They're experiencing some minor challenges in this topic, so I'm really dedicating this entire class, putting together a video for that student to assist them in their Calc 2 course. All right, so now we're going to talk about a new test. We talked about 3 separate tests now. A new test we're going to talk about is called the ratio test. So let's just jump into it. Let's jump into it and attempt to attack this ratio, what's called a ratio test. All right, so this particular problem, what we have is they say we're going to sum from n is 1 to infinity of, we've got negative 4 raised to the n, and this is over n, what's called n factorial. All right, n factorial. In English, factorial means, hey, to say something with a lot of passion. But in math, factorial, what factorial means is if you've got, let's say, 5 factorial, 5 factorial is taking 5, subtracting 5, multiplying that by 4, multiplying that by 3, 2, and then 1. That's what 5 factorial means. 3 factorial would mean taking the initial number 3, multiplying that by 2 and 1, and that's 3 factorial. So n factorial would mean taking n, multiplying that by n subtracted 1, multiplying that by n subtracted 2, and you go on and on and on and on. All right? So, that said, let's talk about this idea of the, let me write down what test we're talking about. This is the ratio test. It's a ratio test. Okay? Ratio test. All right? So, with this ratio test, in my textbook, you find that on page 588. Let's take a look at this ratio test. All right. I'm not going to write all this out. But what this says is what you're going to do is you got another quotient. Let me write part of it out. So what this is saying is you're going to evaluate the limit. You're going to evaluate the limit as n approaches infinity of the absolute value of a to the n plus 1 over a to the n. You're going to evaluate that limit, and then you're going to examine a couple things. In fact, let me write this over here. You got the limit as n approaches infinity of the absolute value a, substituting n plus 1 over a to the n. All right, so let me get rid of this. Sorry about that. I just want to provide, I want to have some room here to do the actual problem. All right. So, after you evaluate this limit, and we'll talk about what a to the n plus 1 means, but if you evaluate the limit and you get something less than 1, well, according to this test, this would be proof that your series a sub n converges. All right. Actually, the theorem says it converges absolutely, but we won't talk about right that. We won't. It converges absolutely, but we'll talk about what that means at another time. And also, in addition to that, if this same limit, if it's greater than 0, if the limit ends up being greater than, I said 0, I meant to say 1, sorry about that. Well, if it's greater than 1, well, that would tell you that the original series, that it diverges. Diverges. All right? Diverges. So again, if you apply this limit and it's less than 1, according to this ratio test, that would tell you that the initial series converges. If you evaluate this limit and it's greater than 1, I just don't feel like writing this over again. If you evaluate this limit and it's greater than 1, according to this test, A sub n, the original series, diverges. And then if you evaluate this limit and it's equal to 1, if it's equal to 1, according to this test, the ratio test is inconclusive. It's inconclusive, which would mean that the ratio test is not the test that you should use to evaluate this series. You would have to begin the process of trying to choose another test instead of the ratio test, because you evaluating the limit, getting the limit is equal to 1, it gives you no direction in determining the convergence or divergence of the series. So all of that said, let's go on and evaluate this series, trying to determine whether it converges or diverges using this ratio test. So first off, what this A sub n plus 1 means is wherever you see n plus 1, wherever you see n, you're going to substitute n plus 1. All right, and you see n here and here. So you're going to have a quotient where the numerator is going to be you substituting n plus 1 here and here, and then the denominator is going to be A sub n, which represents the original series. All right, so let's go on and do the problem. So we got the limit as n approaches infinity, which the ratio test requires. The limit as n approaches infinity of the absolute value of -4 to the n plus 1. Again, I said substitute n plus 1. So you have n plus 1 over, substitute n plus 1 here as well. So we get n plus 1 factorial. All right. And what you're going to do is you're going to divide that by A sub n, which is the original series. So you got -4 raised to the n over n factorial. All right, so we're going to evaluate this limit as n approaches infinity. And as I said before, you're going to analyze the limit, and if it's less than 1, that would tell you that A sub n converges. If you evaluate the limit and you get something greater than 1, that would tell you that A sub n diverges. If you get 1, we have to go another route. All right, so let's evaluate this limit using a lot of algebra. All right, so what I'd like you to be able to see here is we've got a quotient. Not only that, we've got some exponents there that we can expand. So we got the limit as n approaches infinity of -4 to the n plus 1. Another way to write that is -4 to the n power times -4 to the 1 power. It's the same thing because when bases are the same, you can add the exponents. All right? And this is divided by n plus 1 factorial. All right, so n plus 1 factorial. Another way to say n plus 1 factorial, as we said up here, is n plus 1, all right, that would be times, you'd subtract 1, so that would be times n, all right, times n minus 1 times n minus 2, blah, 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 so on and so forth. You'd have you would add an infinite number, or excuse me, you would multiply an infinite number of terms. All right, so let me just write this a little bit neater. So rather than write out an infinite number of terms, what I'm going to do is just say n factorial. N plus 1 times n factorial, which is the same thing as saying n times n minus 1 times n minus 2 times n minus 3. I'm just writing n factorial. You see why I'm doing that a little bit later. All right, so now we're going to multiply that by the reciprocal of this denominator. So up top here, we have the reciprocal of this denominator would be n factorial there, and this would be over negative 4 to the n power. All right, absolute value of all that. All right, we're going to apply the limit of that. And hopefully, what you'll experience, not only on this problem, but on future problems, hopefully what you experience is a lot of cancellation. And hopefully now you see why I, rather than say here, n times n minus 1 times n minus 2 times n minus 3, so forth, hopefully you see why I just put n factorial, which is the same thing. You experience the cancellation, which would simplify this problem. All right, now, and not only you have cancellation there, you have cancellation here. So we got negative 4 to the n here, cancels with negative 4 to the n there. And what you experience now is a much easier problem to evaluate the limit. So we have the limit as n approaches infinity, of absolute value of negative 4 to the 1 power over n plus 1. All right, over n plus 1. All right, so what you experience here, you can pull out any constant when you're working with limits. You can pull out a constant. So what you have here is you have negative 4. All right, so you have negative 4, and this is multiplied by the limit. Well, actually, the absolute value. Because it's absolute value, let's just keep that 4. Okay, because you're taking the absolute value, so you end up with 4. And you got the limit as n goes to infinity. Again, we're taking the absolute value, so we pull out a 4 of 1 over n plus 1. 1 over n plus 1. So hopefully everyone's okay where the 4 came from. We're taking the absolute value of a negative 4, which is 4, so I pulled out a 4 because when you're working with limits, it's okay to pull out a constant. Well, if you evaluate the limit as n goes to infinity of 1 over n plus 1, you get 0. So you end up with 4 times 0, which is 0. All right, so you evaluated the limit. You go back to this sort of the definition of this ratio test again. If you evaluate the limit, you get something less than 1. 0 is definitely less than 1. That's proof that your original series, which is a sub n, converges. All right, so the way you put that into words, you'd say something to the effect that the limit as n approaches infinity of a sub n plus 1 over a sub n, absolute value, because that was actually less than 1. It was actually 0. Because of that, according to the ratio test, you would say that this series, a sub n, converges. Uh-oh. Sorry about that. Converges. Okay? All right.